That's great.
So you're all very welcome again. Fergus Dolan is my name. I work for NALA, and we're delighted to have Sheelagh Clowry here this morning to facilitate a webinar for us on a seamless transition from number to algebra. So over to you, Sheelagh, and good luck.
Good morning, everybody. You're very welcome, and thanks, Fergus, for your introduction. Now, the theme today is a seamless transition from number to algebra. So what I would like for your students is that they would make sense of the mathematics and particularly of algebra, and that they would relate it to everyday life, and also that they would relate it to all the prior knowledge that they have, because adult learners bring a wealth of prior knowledge to the classroom. So we'll get started. And we're going to use some ideas from research. These ideas have proven to be useful for students when they're learning algebra. So the best practice links algebra skills to number skills, and that's what we're going to do today. You will begin algebra with relationships rather than procedures. You will see that in the first activity you're doing. Teach the skills in different ways to reach a variety of learners. So we're going to make connections to number. We're also going to use algebra tiles, and we're going to use area models. Excuse me. Avoid informal shortcuts. So for instance, when solving equations, students often hear, bring it over and change the sign. So that's an informal shortcut, and it doesn't really help to explain what is happening mathematically. Teach algebra as a useful and convenient problem-solving tool. And of course, why else would anybody want to learn about it? And the importance of mathematical literacy. So we want our students to use mathematical terms with understanding. So the basic idea behind today is that we're going to treat number as the groundwork for algebra. We're going to link back and forth between algebra and number. So we'll start with that. Now you see on the screen here a set of consecutive numbers. It's a pattern. And of course, when you have a pattern, you can predict what's coming next. So everybody knows 7 is coming next and 8 after that. But we will ask students, can you write 7 in terms of 6? How is it related to the one before it? So hopefully they will give you this answer, 6 plus 1, and then 8 would be 6 plus 2. And then we ask them, how is 5 related to 6? And hopefully you will get it's 6 minus 1, and 4 is 6 minus 2. Now we're going to generalize this pattern. And let's say we're somewhere in this pattern, anywhere, at some particular number, but we haven't specified the value of that number. So what we do is we use a letter to represent a number. So we're going to call it any letter at all. It doesn't have to be R, it could be any letter. So what is the number after R in this pattern? So we hope students will relate it back to number and say, it's R plus 1, and the next one is R plus 2. And the previous one would be R minus 1. And the one before that would be R minus 2. So in this very simple way, you have introduced the variable, which is a letter representing a number. That is all it is. And it's one of the building blocks of algebra. So we call that a variable. So when a letter or symbol is used to represent a number, it's referred to as a variable. And the understanding is that we haven't yet assigned a value to that letter. So in the previous pattern, that letter represented any number in that list. I'll just go back for a second to think about for a minute what students' concept of variable might be. Now, with the best of intentions, sometimes the variable is introduced to them in this way, particularly when adding like terms, that 1 apple and 1 apple is 2 apples. Of course, that is true. But then a person might go on and say, okay, therefore 1A and 1A is equal to 2A. problem with that is that the student might think that the letter A is an abbreviation of a word. And when we're doing algebra, letters always represent numbers. So I will just show you here where a student had this misconception. So we have here, apples cost a cent each and bananas cost b cent each. If I buy 3 apples and 2 bananas, we ask the student, what does 3a plus 2b represent? Now it's 3 times the cost of an apple plus 2 times the cost of a banana, where the a and b are numbers. So it is the total cost of 3 apples and 2 bananas. But this is what the student wrote. It's 3 apples and 2 bananas. So we have to be careful that they understand that a variable represents a number, not an abbreviation of a word. Now we look at some notation. So we'll double a specific number and then we'll double any number using a variable. So 2 by 5, that's doubling a specific number. You multiply by 2. Now we're going to generalize this procedure. 2 by any number. And we use a letter to represent the number. So this time I've used the letter P because I don't want to be using the same letter all the time. Problem here might arise if we use the letter X. P is any whole number. Now, if I use the letter X, there's confusion there between the multiplication symbol and the letter X. So to avoid confusion, which mathematics always does, we decide to put brackets around each of those, around the 2 and around the X, with no sign in between the brackets. And when you see 2 brackets back to back with no sign in between them, that means they are multiplied together. Now we could leave out the brackets on the 2, so that's 2 multiplied by X, or we could leave out the brackets altogether. So when you see a number and a letter right beside each other, no sign in between, that means multiplication. So the students need to understand that. But of course, we have to be careful. If you write down 25, it doesn't mean 2 by 5. Then we can ask, what are the what are the factors of 2x? So the factors of 2x are 2 multiplied by x. So I'm introducing the word factor here. What is 1 more than 2x? Thinking back to 1 more than r was r plus 1. So 1 more than 2x would be 2x plus 1. 5 less than 2x would be 2x minus 5. Now we look at halving a specific number, like 6 divided by 2. And then we'll generalize it using a letter to represent a number. So n, any number divided by 2, where n is any whole number. How can we write that? Write it that way either. N over 2. Or we could write it as half of n. And of meaning multiply. We know that there is no sign in between the half and the n, so that means they're multiplied by each other. Okay. Now, expressions as pattern generalizers. If you have that expression there, 2p, what does it represent? It generalizes a whole set of numbers because we know that p can take on any value. So we could ask the students to evaluate the expression, notice the language, 2p, when p equals 0, 1, 2, 3, etc. What do I mean by this? Well, if p is 0, this becomes 2 noughts. But if p is 1, it's 2 ones. If p is 2, it's 2 twos. So we end up with a whole lot of possible values for 2p. So that little simple expression can represent all these numbers. So a letter symbol can be used to represent a range of numbers and not just one particular number. Now, I just want to further clarify the word expression. So an expression could be a single term or a number of terms added or subtracted. What do I mean by that? Let's say you write down 8. That's an expression. There's only one term in it, 8, and it's constant. 8 is always 8, not 8x, it's just 8. Here's an expression with only one term. The 3 is constant, and the r is variable, and they're multiplied by each other. Now that could express the 3 times tables, 3 1s, 3 2s, 3 3s. And here's an expression with 3 terms in it, 3r, 5ts, which is 2 different variables, and -8. So we have 3 terms there. 3, 5, and 8 and -8 are constant, and the r's and the t's and the s's are variable. And when there's no sign in between the number and the variables, they're multiplied by each other. Now we refer to the 3r as a term, the 5ts as a term, and -8 as a term of this expression. So we see that terms are separated by plus signs or minus signs. Okay. And we want students to use this type of language because otherwise they won't understand what they're being asked. Now, this cartoon here, look at it for a few seconds and just think about what idea it's getting across. So this is the confusion students have between expressions and equations. An equation will always have an equal to sign. So if you write down x plus 2 on its own, that's an expression, and it can take on a range of values depending on what x is. But then if you write down x plus 2 equal to 5, you now have an equation. The only possible value x can have is 3. So you have confined the variable to one value. So I'm just going to show you, and you can listen to somebody else speaking for a moment about this issue. So equals is what you find in equations. So this is Professor Jo Bowler from Stanford University, and she's Professor of Education. And if you Google her, you'll find lots of interesting ideas from her on the teaching of mathematics. So I'm just going to play you a clip from this. I hope everybody is going to be able to hear it.
I can talk a little bit about algebra. I think algebra exemplifies the problems we have and what a great approach is. So in algebra classes, typically across in many places, they start with solving for x. You open a math textbook, it teaches you how to solve for x in algebra. So that's finding a particular value of x in an equation. That's actually a very narrow piece of algebra. And the key idea of algebra is that this x thing represents a variable, which isn't captured in this solving for x. So we lead kids down the wrong path early on, and they solve for x, solve for x, solve for x, and then they're told x can actually be anything, can be a variable, and that causes a huge conceptual block for them. And that's one of the reasons many kids fail algebra.
Okay, now there's more in that video, and you can watch it yourselves later on. So I'll just move on here. So I hope that idea has come across, the difference between expressions and equations.
So a good algebra task, one I use a lot.
Let's move on here now. Okay, so what we're suggesting here, the advice is start with expressions, just like x plus 2, substitute different values for x, see that you can generate a whole lot of different numbers, and then realizing that if you make an equation, x can only have one value in that particular equation. Now, we've talked about the variable. So now it gets to the stage where you want to see, have students understood what you're talking about? So we ask them, what does r plus s mean? We hope they will say, oh, that represents any two numbers added together. Is it the same as rs? Which means r multiplied by s. And now the very important thing here is verify. How do you verify this? How can you be sure? Well, if you go back to number, which is the theme of this workshop, 3 plus 2, is that the same as 3 by 2? So 3 plus 2 is 5, and 3 by 2 is 6. No, they're not the same. Is R plus S the same as S plus R? Verify. Is 3 plus 2 the same as 2 plus 3? Yes, it is. What does RS mean? That's two numbers multiplied by each other. Is it the same as SR? Is 10 by 2 the same as 2 by 10? Yes. Is R plus 2 the same as 2R? Well, 5 plus 2 is not the same as 2 5s. But if R was 2, it would be the same. So there's one exception here. 2 plus 2 is the same as 2 2s. And you could put context on that. You know, someone is 2 years older than me. So that would be my age plus 2. Someone is 2 times my age. I don't think anybody exists with 2 times my age. But anyway, that's the difference between R plus 2 and 2R. So getting students to generate and explain their own expressions, including variables and constants, that is so important to get them used to using a variable and to evaluate expressions. So you are going to have an activity to do this for your students. Okay, now here's a short activity. And in words, we have any number multiplied by 5. So you would hope that after introducing the variable, that the students would be able to write it in symbols, something like 5f. It doesn't have to be f, it could be 5a, it could be 5x. Any number add 2. Hopefully, here it says something like e plus 2 or a plus 2. Any number subtracted from 8. Take away any number. Any number divided by 3. Any number multiplied by itself. So that one there, p squared, p by p, we call that p squared because it actually comes from a square. The sides of a square are the same as each other, x by x, x squared. And I've written down at the bottom here, John Stewart, and you can check out some of his work as well. So he has lots of exercises like this. Now we could do that exercise the other way around. Give them the expression first and ask them to write it in words. Now we're using some words with brackets. Any number minus 2, all multiplied by 3. Give your students a minute to think about that. So any number k, subtract 2, then all of that multiplied by 3. Any number plus 7, then times 2. Let's see, can they come up with something like that? Any number multiplied by itself, so like p squared, then multiplied by 3, then multiplied by 3. So that's how the brackets are written in English, and take that exercise and turn it around the other way. So you're going to now go to breakout rooms, and Fergus has emailed you a set of questions designed to build confidence in writing algebraically. The students are presented with pairs of questions, and one pair involves numbers and the other pair involves using variables. And they do the question with numbers first, and then they do the same thing using variables. So just before you go to the breakout rooms, I'm going to pull up the exercise here. And the first one is given to you as an example, but I will show you another example here. Number 3, electricity costs 0.17 per unit, and a family uses 656 units in one billing period. So what is that going, sorry, number 2 here. What is that going to cost them? Well, it's the number of units multiplied by the cost per unit, which is 0.17. Sorry, my writing with this pen is a bit wobbly. Now, what if we don't know the number of units? Because that can actually vary, but the cost per unit is not going to vary. So an expression for working out the bill will be 0.17 times x, or 0.17x. Now, if they have a standing charge of 32, that's fixed, isn't it? And this family uses 656 units at 0.17 per unit. There's an expression in numbers for the bill. Now let's use variables here. Well, the standing charge is constant. The cost per unit is constant, but the number of units is variable. So what I would like you to do now until about 11:30 is to, in your breakout rooms, work together on this exercise. So Fergus, can you send, I would love to have given you longer in the room. Thanks very much, everybody, and hope that makes sense to you, and everything will be shared with you. So it will be there for you to use. And I'll also put a set of solutions just to make it handy when you're working with adults. Now, so we'll see there that the best practice links algebra to number, and we had relationships there, you know, the relationships between profit. It takes a minute now for my screen to come alive again after the breakout. So you saw there in business, calculating profit, there was a relationship between selling price, cost price, and profit. You could express that with symbols. Profit is selling price minus cost price. Household bills, cooking, the time to cook a turkey, so much per kilogram plus, 20 minutes over, something like that. You could have it in gardening, where the quantity of soil to fill a box, you measure the units of height, the width, the length, multiply them, you have the volume of the box. And in exchange rates, there are relationships between value of the euro and value of sterling. Decorating a room, how many tiles will I need? So the area of the floor, that's fixed, but the area of a tile could vary. And in health and fitness, calculating a BMI, that's algebraic reasoning, because everybody's weight is different, divided by their height squared. That's the formula for BMI. So we've algebra everywhere, algebraic reasoning everywhere. So just to talk about a bit about adding like terms, and we talked before about maybe the dangers of adding one apple and one apple equals two apples, that analogy. The students might think that a letter was an abbreviation of a word. So what do we do then? Well, use number. So 2 plus 2 plus 2, we know that that's 5 2s, right, as a product in terms of 2. So it's 5 lots of 2 or it's 2 lots of 5. So what about b plus b plus b? Same idea. It's 5 lots of b. And that works for any numbers. 927 added to itself 4 times 927. P added to itself 4 times p. 3 5s and 3 5s. Well, every student will know if you have 3 fivers and another 3 fivers, you altogether have 6 fivers. If you have 3x and 3x, where x is any number, you're going to have 6x. So I'll show you on the next slide an instant where a student is not thinking of the variable as representing a number and the misconception that they had. So here a student was asked to simplify 3x and 3x, and they wrote down 6x squared. Now, no student would say 3 5s and 3 5s is 6 times 5 squared, which is 6 times 25. So they're not thinking of the variable as a number. And it's very important that they go back and check, not only saying to them, this isn't correct, we don't do that, we say, just check it out, substitute in a number, see does it make sense. If it doesn't work for number, it doesn't work for algebra. So the student wrote down here as well, another student, x plus x is x squared. 5 plus 5 is not 25. And then 6 plus x squared is 6x squared. Well, we know from the notation before, 6x squared means 6 multiplied by x squared. But it's so important that students understand the letter as a number. And they can check by substituting in values. Here we have more than one variable, so you can read that yourselves there. 4 2s and 7, 5 2s and 3 7s and 1 7. So we put the 4 2s and 5 2s together. Imagine you have €2, 4 lots of €2 and 5 lots of €2. That's 9 lots of €2. And then you have 1 7 and 3 7s and 1 7. You have 9 lots of €2 and 5 lots of 7. Using letters, variables. So the 4a and the 5a is 9a. And the 1b and 3b and 1b is 5b. But I guess the point here is that these bottom two, the expression here, that this would never appear without something associated with number to explain why it works. And then you have 3 times 2 squared and 5 times 2 squared in terms of 2 squared. Well, 2 squared is just a number. It's 4. So if you have 3 4s and 5 4s, you're going to get 8 4s. Okay, what about if you have 3x squared and 5x squared? You're going to get 8x squared. So make sense of the symbols by going back and forth to number all the time. So we're going to go now to a manipulative called Algebra Tiles, and maybe some of you have used these before, and maybe you haven't. And the research that we talked about before said to teach the skills in different ways to reach a variety of learners. So that's the whole point of this. So I'm just going now to I'm going to do a new share here. So Fergus, when you see the Algebra Tiles, can you let me know, please?
Yes.
So everybody sees them now. So what I'm going to do is just show, maybe some of you know these already, so bear with me because some of you may not know them already. So they are rectangular shapes that are used to represent variables and constants. And when you go into it, you can have colors on or off, and you can have labels on or off. And you can also have more than one variable here. You can have x's and y's as well if you want to. But I'm only just going to show you initially how you could use it, and I'm going to stay with one variable x. Now, what way do the tiles appear? You have unit tiles. Why is that called 1? Its height is 1, its width is 1, so its area is 1, 1 by 1. Now, if we also have a tile x, why is that x? Its height is 1, its width, we haven't assigned a value to it, so we're calling it x. So its area is 1 by x, which is x. And then we have another tile called x squared. Why is that called x squared? Its width is x, its height is x, so its area is x by x, which is x squared. Now you might be wondering about the tiles over here on the right. So they are the negative versions of the other tiles. So if we have -1, and I'll put that over with +1, and they give me 0. Negative x, put it over plus x, that gives me 0. Negative x squared with plus x squared, that gives me 0. Now there's a text box here, and you can type in various things that if you wanted to model expressions with the students. And the students can, of course, go home and try this out themselves. If they're using a mobile phone, they can check something called Mathies, M-A-T-H-I-E-S, and they can download it for free on the App Store. So let's say we want to model 2 plus x. So I'm going to pull 2 across here into the workspace. Now, do you see the copy here? I can copy to the right or to the left, or whatever I like. I'm going to copy that. And I'm going to add on x to it. So that's 2 plus x. So you can see it's 1 times, the width here is 2 plus x. 1 times 2 plus x. Now let's look at 2x. Does that look the same? So there's an x, and there's another x. There's 2x. So it's a height 2 and a width x. So there's 2x. Not the same as 2 plus x. Now there is one instance when x is equal to 2. We talked about that before. But in every other instance, they are not the same. And then we look at x. We could model 2x this way either, using vertical ones. So the height is x and the width is 2. Now here's x squared. Let's try 2x squared. What does that look like? X squared and x squared. Why does that work? Well, you have a height of x here. What's the width? X plus x. You add the lengths together. So you have 2x by x, which gives you 2x squared. Now, it may take time for students to get used to doing this. And I'm only showing you initially a few things. I'm going to do one more, 2x plus 4, model that. So 2x and 4, okay, I'm going to use the copy function here. Copy to the right, copy down, copy to the left. Now, look at this expression 2x plus 4. But I can see it's also 2 times x plus 2, which is the same as 2x plus 4. Now, if you've never seen algebra tiles before, you'll need to open this, and just play around with it for a while. And there are lots of little videos and, PDFs which give you help on it as well. Has anybody used algebra tiles before?
No.
Okay. So anybody can answer here. Do you think they might be useful?
Yeah, they look very useful for visual
Yeah, I
learners. Yeah.
Yes, and everybody to a certain extent is a visual learner, aren't they? Okay, so I'm going to do, if that's okay now, I'm sorry, it's just a brief taster. I'm going to go back to my PowerPoint here for a minute. And then you're going to be in a workroom together again, shortly. So there's search for Matthews in the App Store for the students. I tried it on my phone last night and it works. So multiply 5 by 6 using an array model. I'm just talking about this area model here again to link to the algebra tiles. So there's 5 by 6, but we could split that up, couldn't we, into 5 by 4. If you had a room 5 by 6, you could make 2 rooms out of it. So what are we saying here? 5 by 6 is the same as 5 by 4 plus 2. Same area. But that's also 5 by 4 plus 5 by 2. Now here you have something that you come across in algebra called the distributive law. But I mean, it's no big deal. It's just common sense. So we can see that all of these are equal to each other. And you can work backwards. You can start on the right-hand side. And 5 is a factor. So the dimensions on the left-hand side, they are the factors. Name one pair of factors of 30, 5 and 6. So let's look at, now go to algebra, 5 by x plus 2. Okay, there's my length, x plus 2. So we could split that up into 2 parts, 5 by x and 5 by 2. Okay. So here's our distributive law again. 5 by x plus 2 is 5 by x plus 5 by 2. Okay, you can multiply it out. It makes sense. Nobody has to teach you about this. And we can start on the right-hand side and work left. Doing and undoing is a very important concept in algebra. So we've multiplied. Now can you work backwards? Well, that's 5 times x plus 5 times 2. So the factors are 5 times x plus 2. The factorizing shown there. And it's just common sense. And there's how you would show it using algebra tiles. And you can do similar examples. I've just put one there. And this is one I showed you. Explain why the area of this shape is 2 times x plus 2 and 2x plus 4. Well, we can see the height is 2 and the width is x plus 2. So it's 2 times x plus 2. But this bit of it is 2 times x plus this bit of it, which is 2 times 2. And there's using algebra tiles. Okay. I'm going to get you to work together now in a minute, but first of all, show you, here's a student who was asked to multiply 2 by 2x minus 5. They really were just thinking rules, I think. They weren't thinking back to having had the experience of 2 times x minus x plus 2, and they only multiplied the 2 by the 2x. So it's very important not just to say multiply by the number outside the bracket. Make sense of that with diagrams. Okay, and how do you know if you're correct? Well, put in a value for x on the left. And how do you know if your answer is right? Put in a value for x on the right. If they're not equal to each other, your answer is not correct. So self-correcting, and you know, the teachers or students are not dependent on you. They're able to figure out for themselves if they're right. Now here's your next activity. And this is the last activity that we'll be doing in the breakout rooms. So I'm going to just explain it to you briefly first. On the left-hand side here, you have an area model. So you can look at the first one here, and it's 3 by n plus 4 by 1. And this one here is 2 by n plus 2 by 3. You will be asked to match the words with the area model. That's going to be on one page of the Jamboard. And then you'll be asked to match the algebraic expression with the area model. So we can see down here 3n plus 4. That one matches with the first one. And they're the words that match with that. So think about your students when you're doing it. When we go to the Jamboard, I thought we might have 8 rooms, but we've just 4 rooms. So if you're in room 1, you're going to be using frames 1 and 2. So maybe jot that down. If you're in room 2, you're going to be using 3 and 4. Room 3, you're going to be using frames 5 and 6, and room 4, frames 7 and 8. I'm going to go to the Jamboard now, and Fergus, if you put the link to the Jamboard into everybody's chat, please, or into the chat for everybody before we send the breakout rooms. And then,
yep, the Jamboard link is in the chat.
That's great, thank you. And I'm going to go to that Jamboard link as well. Now to do a new share. Okay, and you should be seeing the Algebra Tiles, are you, Fergus?
Yes.
Yeah, so I'm going to go now to the Jamboard. Now, if you haven't used Jamboard before, I'll explain it to you. And once I've explained it to you, you can go into the breakout rooms. Okay, here we are. Now, it's just like a whiteboard. So what you can do when you're in there is you can click on, say, this word expression, which add 3 to n, then multiply by 2. Okay, where is that? So that's that one. Add 3 to n and then multiply by 2. So that's the word expression for that. And likewise, you match all the other word expressions with the area model. So then you go to the second frame. See where I'm clicking up at the top? And now you match the algebraic expression to the appropriate, I'll pick a different one here. Say this one, n over 2 plus 6. Where is that? So that's this one. And if you do that for the two.
I think they're all done now.
You're very, very welcome back. We're coming to the end, and of course we need more time. We do more activities, but hopefully you got something from those activities. I have found them to be useful with all ages of students. So hopefully that will be the same for you. Now, just look at what's on the screen there. And from what we have done, do you think your students would be able to do the first part? Right, so the cost of hiring a plumber. And then I just briefly look at the second part because we didn't get time to solve the equations. So there's an expression. We charge you €50 and €30 per hour, €50 to come out of the house. But you only have €200 to give him. So now we're in the situation where you have put that equal to 200. So there can only be one value of h for that. How many hours can you afford? So one of the things I said earlier was to avoid informal shortcuts if at all possible when you're solving equations. Nobody has to teach you how to do this. The students will be able to do it in their heads. They'll take 50 from the 200 because they have to pay that anyway. So we can say we're subtracting 50 from both sides of the equation. That'll give you 30h equals 150. Now work backwards. How do you get h? Well, you multiply it by 30, get 150. So use the inverse operation, divide both sides by 30, and h is equal to 5. But before you put this up, ask students, can they work that out? And they will be able to work it out in their heads. So hopefully you have learned from today. Does anybody have anything that you'd like to say or to put in the chat, or any questions before we finish up? And I want to thank you very much for engaging with the activities.
Sheelagh, can I ask you something just?
Absolutely, yes.
A lot of people use this more modern way of, I was taught the way you have that last equation, like 50 plus 30, it equals 200. But a lot of people now, they will add on the 50, they'll put 50 on both sides.
So I agree. So what I am saying that, you see, they subtract 50 from the left, so they subtract 50 from the right.
Yeah, but do you actually visibly show that, like take the 50, you know?
So you can do that. And if I had more time, I would have probably written in those lines.
No, I actually find it easier to do it this way, but I was wondering, would students find it easier to see? I was never taught the other way, to add it in and take it away.
So subtract, what do I say? Can I write on that slide now and move that back there? Have we half a minute, Fergus?
Yeah, absolutely.
And
I wonder, does most people just skip that bit, or do they put it in?
Now, you see, nobody really skips it because you're actually doing it in your head. You're working backwards.
Okay.
So you know that the last thing that you multiply the number of hours by 30 and then you added 50. Now work backwards. You're going to subtract 50 from that, aren't you?
Yeah.
So if you subtract 50 from one side, you have to subtract it from the other.
Yeah.
That brings you down to here. So initially, I might write that in for the students, but I don't expect them to write it all the time. But I do expect them not to say, bring it over and change the sign, because that is mathematically not teaching them anything. So they subtract 50 from both sides. Now you're down to here. How do you end up getting h? Well, 30h equals 150. I'm working backwards. I multiplied h by 30, so now I divide both sides by 30. So what you're saying, Bridie, Bridie?
Yeah, that's right, Sheelagh.
Yeah, okay, Bridie, is yes, you can write it down, but saying what you're doing is very important, and gradually they can drop that.
Yeah, I like the way you use the vocabulary, the constants and inverse, etc. It was very well done. Thank you.
Thanks very much, Bridie. Thank you. Yeah, and it's, you know, students should be encouraged to use the correct vocabulary from the beginning. Okay.
Sheelagh, there was a question from Siobhan O'Keefe asking, could you repeat again the names of the apps? So I think I wrote one down. Mathies, was that correct? M-A-T-H-I-E-S?
It's Mathies, and I can, now that I have my pen, I can write here on the screen.
Please, thanks.
Even though I hope you can read this writing.
Yeah, we can read
and
it.
It's free in the Mathies Algebra Tiles, and it's free in the App Store.
Thanks. And was that the only one, the only app you mentioned, yeah, during the
that
webinar,
was the, yeah, it's perfect. You could use Algebra Tiles. Now, look, if you go on the internet, you'll find hundreds.
Okay.
Literally. But these are ones that I have looked at and I have checked, and I can vouch for them.
Great.
You know, but better things are always coming on the line.
Okay. Well, Sheelagh, I think that just would bring us to the end then. There's a lot of people text or put in the chat. Thanks very much for a great presentation. Really enjoyed that. So it just leaves me to say thank you very much, Sheelagh, for a fantastic presentation. You're always so well prepared and your delivery is so calm and explain well and use plain English. So thank you. It's much appreciated. I can see from the chat bar that people are delighted with it. So thanks all. And I will be, Sheilagh's going to send me on her slides and I'm going to send them out to all of you. So I hope you got something from this. I know an hour is short, but we were trying an hour and a half webinars and people said they were a bit long. So it's just hard to know. So anyway, thanks Sheelagh, and thanks everyone for tuning in. I hope you enjoyed it.
And the Jamboard link as well, you have it, you can use it.
The Jamboard link there as well, and if anyone needs it again, they can email me and I'll resend it to them. Okay.
And if anybody
Thanks,
wants
everyone.
to ask me a question now and somebody else wants to, you know, that's fine. But
Pardon, Sheelagh?
if anybody wants to ask a question.
Yeah,
now,
if anyone has a question now, they can unmute and ask Sheelagh.
and everybody can leave if they want to, you know.
Or if you're in a hurry to leave, you can leave.
Okay.
Okay, there's Laura DeMilla saying thanks, great app suggestions, including the Jamboard for learners too. Yeah. And Padlet, if you've used Padlet, it's like the Jamboard.
Yes.
So I think we leave it there, Sheelagh. There doesn't seem to be questions coming in.
That's
Thanks
great.
again, Sheelagh. All the best to everybody. Bye-bye. Oh,
Bye,
by the way, we've webinars all week. So tomorrow we've got fun and practical approach to teaching geometry. That's at 1 o'clock. And on Wednesday, we have developing conceptual understanding of key concepts in financial maths. That's at 1 o'clock. On Thursday, we've helping adults overcome maths anxiety, and that's at 1 o'clock. And on Friday, it's earlier. It's at 11 o'clock. We've got analyzing errors and misconceptions in maths. That's 11 on Friday. So if there's any other webinar that you haven't booked into and you'd like to, they're all free and we'd be delighted to have you. So thanks everyone. Bye-bye. Thanks, Sheelagh.
Okay. So